So let's talk about something that's, well, absolutely critical in any modern data center. How do you protect your virtual data from a very real, very physical threat? Today, we're going to dig into how VMware's vSAN answers that exact question.
I mean, really think about that for a second. All your precious data, your applications, everything, it all lives on physical servers, on physical drives. What's stopping someone from just walking out the door with one of those drives? How do you make sure that what they're holding is just a glorified paperweight and not the keys to your entire kingdom?
Well, the answer, and it's probably not a huge surprise, is encryption. It's all about scrambling your data into complete gibberish so that only the right systems, with the right keys, can ever make sense of it. This is your fundamental line of defense against a physical breach of your digital world. And thankfully, VMware has a really powerful, built-in way to handle it. So let's dive in and meet vSAN Encryption Services. Now, this isn't just one single feature you flip on. It's actually a whole suite of tools that gives you two distinct and really powerful lines of defense for your data. And here they are: Data-in-Transit and Data-at-Rest Encryption. The cool part is you can enable them independently, or you can use them together for, maximum security. And it's all configured on a per-cluster basis. So what's the difference between these two? Okay, first up, we've got Data-at-Rest. The easiest way to think about this is like a digital safe for your files. The very moment your data gets written to the physical SSDs or hard drives in your servers, bam, it's encrypted. It just sits there, completely scrambled and unreadable, until an authorized process needs to access it. And then we have its partner, Data-in-Transit. Now, if the first one was a safe, this one is like an armored car for your data. As your information is zipping across the network between the different hosts in your vSAN cluster, this service wraps it all in a layer of encryption, protecting it from anyone who might be snooping on the network.
And you should know this isn't some flimsy tacked-on feature. Both of these services are built on a cryptographic module that is FIPS 140-2 validated. Now, that's a U.S. government security standard, which is just a fancy way of saying you're getting serious enterprise-grade, heavily tested security that's baked right into the core of the hypervisor. Now, turning on encryption is one thing, but how it's implemented, that matters a lot. And this brings us to a really critical architectural choice that has a huge impact on performance: the original storage architecture, or OSA, versus the newer, much faster Express Storage Architecture, also known as ESA. So, with the old way, OSA, encryption happens at the very last second, right before the data hits the disk. And it has to do this on every single host that's storing a copy of that data. But with ESA, it's so much smarter. The data gets compressed first, and then it's encrypted just one time, way up at the top of the stack. Let me show you what I mean. This slide just lays it all out perfectly. See the green arrows for ESA? All the data services, compression, encryption, checksums, it all happens high up on that first host. That means less data gets sent over the network to the other hosts. Now look at OSA. Those processes are happening way down low on every single host that holds a piece of that data. You can see how that would add up. And here is the big payoff. By encrypting only once, way up high in the stack, ESA just massively reduces the I/O amplification and the CPU usage across your entire cluster. You're not burning cycles encrypting the exact same data multiple times on different machines. The bottom line is this: ESA makes encryption way, way more efficient. Okay, so we've decided we're going to encrypt our data, and we're going to do it the smart way with ESA. But let's be real, encryption is completely useless without the keys. This brings us to the next big decision. How are we going to manage the keys to our digital kingdom? You basically have two main options here. First, you can use the vSphere Native Key Provider, or NKP. It's built right into vCenter, so it's a much simpler, more integrated experience. Or, for bigger, more complex environments, you can connect to an external, dedicated key management server or a KMS cluster. But, whichever provider you end up choosing, the way it works under the hood is pretty fascinating. It's not just a single key that locks up everything. There's actually a really clever hierarchy at play here that gives you both security and scalability. So it works like this. First, your key provider. Doesn't matter if it's the NKP or an external KMS, it creates a master key. This is called a key encryption key, or KEK. Think of this as the master key to a giant safe. Then, for the actual data, vSAN creates a whole bunch of individual data encryption keys, or DEEKs. These little guys do all the heavy lifting of scrambling your data. The KEK's only job is to encrypt or wrap all of those DEEKs to keep them secure.
And what I love about this slide is how it visualizes that whole flow. You can see the external key provider passes that master key, the KEK, down to the ESXi host. The host then uses that KEK to safely manage all the DECs, which in turn are used to lock and unlock the actual data sitting on the disks. It's a really elegant two-tiered system.
All right, so we've got our data encrypted and a system for managing the keys. We're secure, right? Well, almost. Now we have to talk about building a safety net. How do you make absolutely sure you don't accidentally lock yourself out of your own data?
This is the million-dollar question for any encrypted system, and it's one that should probably keep you up at night. Your hosts need to talk to that key manager to get the keys to unlock your data. So what happens if they can't reach it during a reboot or some kind of network outage?
This is where you can get into a really terrifying situation, a classic catch-22, a dangerous circular dependency. Just imagine this. Your key manager is a virtual machine, and it's running on the exact same vSAN data store that it's supposed to be providing keys for. If you have a power outage and the hosts reboot, they can't mount the data store because they need the keys, but they can't get the keys because the key manager VM can't boot up. See the problem?
And this brings us to the solution, the hero of this story, key persistence. And it's all thanks to a tiny piece of hardware called a Trusted Platform Module, or a TPM chip. When you have a TPM 2.0 chip physically installed on each of your hosts, that host can securely cache the encryption keys locally, right on the motherboard. So if the key manager is offline during a reboot, no big deal. The host just pulls the key from its own secure TPM chip and gets back to work. It is the ultimate safety net.
So let's put this all together. If you want a setup that's both secure and resilient, here are the key takeaways. Number 1, choose the express storage architecture for efficiency. Number 2, decide on your key provider, whether it's the native one or an external one. And most importantly, and I can't stress this enough, make sure every single host in your cluster has a TPM chip. That is what breaks that scary circular dependency, and it is the absolute best practice recommended by VMware.
You know, the source material really sums it up perfectly. The whole point here is to provide prescriptive security when and where you need it. It's not about just mindlessly flipping a switch. It's about making deliberate architectural choices to build a system that is fundamentally both secure and resilient. At the end of the day, protecting your data from physical theft isn't just a feature you turn on. It's an architectural decision that requires real planning. So now that you understand all the pieces of the puzzle, the real question is, are you ready to build security into the very foundation of your environment?